Okay, we're live. Good morning, everybody from, I guess, Manitoba West, and good afternoon to all the rest of you to the East. Thanks for joining in for the CUIIC Academy Underground Infrastructure Education presentation today. We're going to have a presentation on assessing health risk associated with CIPP. CUIIC Academy, if you aren't overly familiar with it, is organized by the Canadian Underground Infrastructure Innovation Centre, the University of Alberta, and Benjamin Media. The CUIIC Academy offers classes, courses, webinars, and other events to help further underground infrastructure educational opportunities across Canada. We think this is going to be a really good forum, and this is the first of our planned presentations. We'll be covering a variety of topics related to underground infrastructure. Some of the speakers will be, all of them will be industry-leading professionals who will provide these monthly free educational webinars to the public through CUIIC, and there will be a question and answer period at the end. This will happen every third Thursday of the month at 1 p.m. Eastern. And you can go to the academy.cuiic.ca website to take a look at the overall schedule. So for this webinar series for 2023, we have, there's an opportunity to sponsor, and we'd like to thank MPipe for stepping up and to be the first sponsor for the series for this year. Thanks very much for that. If anyone else is interested, you can contact Hannah Stokulich at Benjamin Media. Her contact information is here, and if you need any more information, we can certainly get it to you. For an introduction, we have Dr. Mark Knight. He's a professor at the University of Waterloo. He's an industry leader in the area of municipal underground pipeline design and construction using trenchless construction methods. He's also the past executive director of the Center for Advancement of Trenchless Technologies, or CAT. And he has a consultancy firm, and he's developed a number of industry-leading tools that have been retained for complex designs, and he's also been involved as a litigation expert. I've had the opportunity to work with Dr. Knight on several occasions, and I'm sure you'll find him interesting, and yeah, that's the pace. You'll find him interesting and knowledgeable. So with that, leave it to you, Mark, to take over.
Hey, thanks, George, and it's a pleasure to be part of this of CUIIC, the CUIIC Academy, and to kick off the 2023 series with a presentation. So I'm going to start. I'm going to give some background information. So I'm going to assume that some people on this webinar aren't very familiar with some of the key components of CIPP. So we're going to go on a bit of a journey. But I'm going to start with, have you heard of this band? The band of dihydrogen monoxide. So this is a website that was created by a individual with a specific purpose, and that purpose is to show that you can take anything that is not really a toxic issue and make it sound that it's really bad. Dihydrogen monoxide is dangerous, and they give all kinds of different reasons why it is dangerous and why it should be banned. I encourage you to take a look at this site if you have not seen it before. If you're not familiar, hydrogen oxide is water, H2O, which is critical to life, and so they do a really good job of taking the chemistry and making it look bad. I would argue that there some pseudoscience has also been used in the industry to highlight, much like this website, some of the negative things without providing all the factual information around health risk with respect to CIPP. So hopefully we'll be able to clarify some of that information today. If you have questions, please feel free to put them in the chat, and we'll do our best to be able to answer them afterwards. Who here, if you're on part of this webinar, has pumped gas and put gas in your car? If you have pumped gas, I'm quite sure that you have smelled the gasoline and you have a health risk exposure to the gasoline. So if you've had a health risk exposure, did you know that gasoline is a known carcinogenic chemical? So it will cause cancer and is called a carcinogen material. So why is it that we are actually allowed to pump gasoline and put gasoline in the car and have that health risk exposure? And the reason is health risk exposure is not just the concentration that you smelt, it's also multiplied by the exposure time. And so if you have a long exposure time at a certain concentration, then we have an opportunity to, over time, develop cancer if it's gasoline. So we have to use a health risk matrix, which is really exposure time on one axis and the chemical concentration on this axis. So we have to do the exact same thing for CIPP. If we're going to be exposed to some chemicals, we have to know what the exposure time is and that concentration, and is that at a level that is acceptable or not. We can also have an exposure time or a concentration that's very high, but it may only be for a very short period of time, minutes or say less than 10 minutes. At those concentrations, it may be okay. So if our exposure time is low and certain concentration, we can estimate what our health risk is. So we're going to apply that same process for the CIPP understanding. But before we can do that, I think it's important we understand what CIPP liners are made up of. They are a fabric material that is wet out with a liquid thermoset polymer resin. So what we're going to do is we're going to take some fabric, needle punch fabric for gravity applications. We're going to use that as a carrier to put this liquid thermoset resin in, and then we're going to cure it in place and turn it from a liquid into a solid. Now, not all thermoset resins are the same, and we have different resins for different applications. We have different resins for potable water. We have different resins for force mains and sewers. We have different resins that are used often for gravity sewers. So it's important that we understand what we're talking about here. So we're going to quickly go through the different types of thermoset resins. So CIPP liners, as I said, are liquid thermoset resins that are cured. And when I mean cured, what's going to happen is a chemical reaction. It's going to occur. It's going to go from a liquid to a solid, and we call that polymers are going to cross-link to form a solid hard CIPP liner. And we need some form of energy to be able to do that. So we can use a part A and a part B and mix them together, and then that will start that cross-linking to occur. If you've ever made fiberglass or mixed up epoxy, where you've got a tube to be able to glue something back together, that is an ambient cured resin. It's a thermoset resin that's ambient cured, and it will kick off and be hard within a certain period of time, depending on how much hardener you put in. We can have a resin where we use a hot water cure to change it from a liquid to a solid. We now pretty well use steam cures because they're faster and can get in and out faster than the traditional hot water cure. And also we now have UV cures that are quite common to be able to cure the resin. So we need to be able to look at those. So we're going to go from a thermoplastic liquid to those cross-linked thermoset solids, which is important to remember. So we look at different types of resins for potable water. Potable water resins that are used for CIPP liners that are used in the drinking water industry for the relining of potable water mains and pressure liners have to go under strict NSF or ANSI 61 drinking water testing requirements to make sure there's nothing hazardous that's going to leach out or come out of that liner over a period of time. So they're strictly regulated and tested. These are epoxy thermoset resins that have 100% solids, and they contain zero styrene. So if there was styrene in these resins, they wouldn't be able to meet the drinking water requirements. And the thing to remember, these are often the most expensive and a little bit more difficult to be able to work with, but that's typically what's used in the water industry. So they're very different than other ones that are used. We go into force mains. Typically the resin that will be used is a vinyl ester thermoset resin. And the reason we want to be able to use that, it has better fatigue resistance because of the pressure on the force main goes on and off, and we need the fatigue resistance of those. So we're going to use a vinyl ester thermoset resin, and they may or may not contain styrene. But vinyl ester resins cost less than epoxy resin cost per pound. But on that side. So typically force mains will use a vinyl ester resin. For gravity sewers, the ones that are most commonly rehabbed, we use what's called an unsaturated polyester thermoset resin, and that often will typically contain somewhere between 30 to 40% styrene in the liquid resin within the liquid resin. And the reason we add styrene is we need the viscosity to get the material to wet out into the fabric. We also need it to make sure that when we pull it in, that the resin stays in place. So we need that viscoelastic behavior. It will create good mechanical properties. And we know from years of experience, it's a very stable and consistent cure reaction. So we know that we're going to get the mechanical properties that we want to get. Now, compared to epoxies and vinyl esters, these are the lowest cost resins. But they're also one of the most commonly used industrial applications. So it's not a specific resin for CIPP. It's also used to make composite pipes, GRP pipes. It's also made tanks, fiberglass, automotive parts, and it's actually the styrene that when you buy a car, those plastic parts that gives you that nice new car smell. That nice new car smell is a little bit of styrene that's in that new car. So if you look up styrene and the use of it, it's quite common. So what does styrene do? Well, what we do is we take unsaturated polyester, we add some peroxide initiator, and that creates that OR. And then we have styrene that's in the liquid. And then when we add heat or some form of energy to create that cure, that styrene gets used up and gets changed in a chemical reaction to be able to create what is the solid, the cross-linking. So the styrene is critical to be able to get those cross-linked in the solids, and it is going to get used up during in the curing process. So most of it is gone from a liquid phase into a solid phase, and it's no longer styrene anymore once it's done. So if we've got a good cure in the liner, the majority of it is used up and is not available to move. Now there may be a little tiny bit left, and that's why we can smell it for a period of time on that side. So styrene does get used up. So it's not, even though we had 30 to 40% in the liquid form, when it's finally cured, we're going to have a little tiny bit, and it's going to be locked. If there is any, it's going to be locked inside that structure, not free to move and move out. Styrene does have a distinctive odor. It is the main chemical that is of interest with respect to health issues. There are some other low-level chemicals, but those chemicals are in these polyester resins are used, the same ones for manufacturing tanks and other fiberglass applications in automotive parts. And there's nothing else in there that's really going to create any issue with respect to worker safety and exposure issues that they have to worry about on that side. Now, the styrene, we can smell at extremely low levels, 0.1 ppm, 0.1 ppm. So we can smell at an extremely low level. So try to remember 0.1 as our threshold level where we start to smell ppm, and then we'll compare that to concentrations that we can actually have, and therefore we can actually start to look at our potential health risk. Unlike gasoline, they're not sure whether styrene is a carcinogen or not, but it's reasonably anticipated that it could be. So it is classified as a potential human carcinogen. So it's a potential carcinogen. And so contrary to many people statements, if you look at the EPA site and you look at other places, it's actually a anticipated or potential carcinogen, unlike gasoline. So it could be or it could not be. And that, again, I think is an important thing to remember. EPA has acute exposure limit guidelines. NIOSH has also other worker guidelines. So there's lots of worker guidelines around for manufacturing in the plant. There's not a lot for public and other people in exposure limits. The best ones right now to use are the Environmental Protection Agency acute guideline limits. And they have AGL1, AGL2, and AGL3, and it's important that we understand what these are. So at AGL1, which is the lowest, it says that at AGL1, the effects are not disabling and are transient and reversible upon the stopping of the exposure. So if we're at or below AGL1, we may have experienced some noticeable irritation and some discomfort, but it's not really a health hazard at that concentration over a given period of time. AGL2 means that we're going to experience irreversible and other serious long-time adverse health effects or have an impaired ability to escape. So at AGL2, it's much more serious. We're going to have some long-term health effects. It's kind of maybe like getting COVID. We're going to have some long-term health effects, and we may not be able to have good judgment, maybe like carbon monoxide poisoning where you get exposed to certain levels, we may not be able to get out. AGL3, you could experience life-threatening effects and or death at AGL3. So we need to now look at these AGL limits. And if you look at the guidelines, there's an exposure time at the top, and then there's concentration so that we can look at our exposure risk and our health risk. So at AGL1, it's 20 parts per million. For a 10-minute exposure, it's 20 parts per million. For a 30-minute exposure, it's 20 parts per million for an 8-hour exposure. So if we're exposed at less than 20 parts per million for 8 hours a day, we will maybe have some irritation, but there's no long-term and there's no immediate health thing, and those things will go away. At AGL2, for a 10-minute exposure, we can go up to 230 parts per million. And for an 8-hour, we're down to 130 parts per million. Life-threatening concentrations for a 10-minute exposure is 1,900 parts per million, as well as for 30 minutes. And if we have exposed to 340 parts per million for 8 hours, on that time frame, then it could be life-threatening on those sides. At the bottom of this table from this EPA site, it says that the level of exposure that distinct odor is noticed is at 0.54 parts per billion. So less than 1 part per billion, we have a strong, distinct odor of styrene. So let's compare that We can smell at 0.04, but our AGL limit is 20 parts per million. So we can say that smelling styrene is like having a canary in the mine. The canary is going to die before us. It's going to give us a good indication well before our exposure limit of AGL of 20 parts per million. At 230, where we may have some long-term effects, you won't want to be in that area at that concentration. You will want to flee and you will want to leave, especially for in less than 10 minutes to be exposure. So at high concentrations of 1900 for 10 minutes that are death-threatening, you really won't want to be there at AGL2 or even close to getting to 20 parts per million. So that's good news. Good news is that we will want to flee. We'll be very irritated when we get to even 10 parts per million styrene concentrations. So what are the exposure risks from CIPP to the public and possibly to the workers? Well, the liner is typically wet out in a wet out facility and shipped to the site in a refrigerated truck. And when we open up that, styrene concentrations will be fairly high inside that truck. And when we open up that door, if you've ever been on a job site, and that truck is refrigerated to make sure that the liner doesn't cure and see any heat and start that chemical reaction of cross-linking. So you'll get a strong smell of styrene associated. And right now, NASCO and the Trences Technology Center is doing a study in order to measure those concentrations that are in that truck and to be able to understand those and the health risk associated with worker safety around that site. Now, if you're worried about health risks, one thing we could do is wear proper protective equipment when you're working around or inside that truck. So that's often a quite recommendation. We can also be exposed to styrene emissions during the curing process of developing our liner, so either using hot water steam or possibly even UV. And so those emissions can come out of the termination points or the exhaust stack. Now, after a line is done and cured, that we often will, in a sewer line, will have laterals that go into businesses and homes. And if there is styrene that's released, it can go up those laterals, and you can people can smell it into buildings and homes during or after the CIPP process. And that is an area that I worked on with a study with Aegon and Dennis Piven, who I think is on this as an attendee here. I just want to let you know that NASCO and TTC has looked at the emissions from CIPP applications and those fugitive emissions, and I'll talk a little tiny bit about that at the very, very end. This year, we published a paper in ASCE publication on styrene migration field study and some of the key findings. If anybody wants a copy of this paper, please feel free to email me. I will send you a copy. It's free. It's open access. Insituform paid to be able to make sure that this is open and available to the public. So what we wanted to do was look at the styrene emissions that could happen through a lateral that is filled, that has a water trap that's filled with water, or a P-trap that's filled with water. So often what happens is an open conduit that's to the sewer, a CIPP liner goes in, and those emissions can transfer up that lateral and into the basement or into the house, especially if it doesn't have proper plumbing. A plumbing code requires that there is a P-trap drain in the basement, and that drain is filled with water. So we wanted to look at those both case scenarios to see the impact. So what we ended up doing was building a mock network that we were going to put a CIPP liner in. We tried to make it as representative as we possibly could. So we did this down in Chesterfield, just on Insituform's property. And then we put in a clay pipe with PVC laterals that are approximately 30 meters long or 100 feet. And then we had on one side of the to the left-hand side is dry traps, and on the downward side or the right side is traps that were filled with water. And what we wanted to do was monitor styrene emissions in those laterals at different locations, and A, which is next to the main, B, C, and coming out of the traps using a variety of different technologies that I'll talk about, so standard technologies. So there's our field site, which is at AGON headquarters in Chesterfield. There's a label of the lateral connections with A being closest to the main, and then coming out to the trap. And what we could do is put in sensors inside with these inside the standpipes and measure concentrations. So we measured with a standard photoionization detector the concentrations inside the laterals, as well as using 3M OVM organic vapor monitoring devices that are used for worker health and safety. It's just basically a charcoal filter, and that absorbs any styrene or any chemicals around, and you send them off and they'll give you a styrene concentration for the time that sensor was open. We also used a new device that was developed at the University of Waterloo for the first time. It's called a Waterloo membrane sampler. It's a patented device that is available through Serum's laboratory in Guelph, Ontario. This is commercially available. It's a relatively cheap device. Cost maybe about $100 for the device and to get an analysis. And basically, it's a special membrane where the chemicals can go in and absorb onto the charcoal, and then we can do a standard gas chromatograph analysis on the material that's on the inside and find out whatever chemicals that came in, such as styrene. So it's a passive sampler designed for sampling of gas vapors for sites. So lots of work has been done on it. It's commercially available. So what is a PID? A photoionization detector is the most common device that's used in order to be able to measure VOCs, volatile organic carbon compounds at low concentrations. And it works very well for measuring volatile organic carbons, which styrene is a volatile organic carbon. It is very sensitive to a broad spectrum of monitors, so it does detect low levels. If you call the fire department will come with their device, and that is a PID to measure if there is carbon monoxide or any other chemicals that are in your house. It does give you an instantaneous concentration at a period of time. But that is not a health risk exposure. We would need to know what those concentrations are over a length of period of time, and then compare those to be able to get our health risk exposure. So this device does not measure styrene. It does measure a volatile organic carbon. So if there's a mixture of gases that are carbon-based, we will get those concentrations. They're also calibrated using isobutylene, typically as a gas, so it is number of concentration of isobutylene on that side. And we'll talk a little bit more of some of the challenges of using one of these devices to estimate the styrene concentration later on. So what we did was, before we installed the liner, we put the PIDs in and we measured the VOC concentrations in parts per million at a variety of different locations. So 15A is lateral number 15 in my initial diagram, and that's next to the main. And you can see that that's got VOC concentrations that are over 100, somewhere around 120 parts per million. On the bottom axis is time from the CIPP liner being installed, and it's negative. So this is 15 or up to 18 minutes before we installed the CIPP liner. So we have high VOC concentrations in this liner that are, if it was styrene, some of those would be around AGL level 2 concentration, which was 130 for 160 ppm for 10 to 30 minutes. You see 15C, which is farther away, was just before the trap on the other end. Again, we have these high VOC concentrations, and these exceed AGL limits of 20 ppm. We've got some other ones. You can see 15PDT, that's the trap, and it's dry. D is for dry, so that was a dry trap. And you see that those concentrations of VOCs are well below of 20 ppm. So what we can do is we can take our PID VOC concentrations and we can convert them to a styrene concentration, provided that we know what the gas is or the mixture is. If it was pure styrene, we would multiply by a factor of 0.43. So if we have a PID VOC reading of 100, and we had styrene in the as the mixture of the gas and only styrene, then the styrene reading would be 0.43, so it would be actually 43 ppm, even though the device is reading a 100 VOCs isobrutally. So what I did in this case was I just took all the VOC readings, multiplied them by 0.43, and you can see that we again in 15A well exceed our AGL1 limit, and we have not even installed the liner. What is not styrene? This is not styrene that's in these laterals. This is the glue that's being used, that we use to put together and glue sections of pipe together. So again, it's not styrene. It's other VOCs that are there. So we really we know that there's no styrene in this location. So again, that's misinformation if we think that it was styrene. Once we installed the CIPP liner, what we wanted to do was measure the levels. And what we can do is use the PID as a reference tool if we know that there is a styrene release. If we do see that there's an increase in VOC readings, and we know that there was a styrene release, then we know that that increase is in VOCs is typically due to styrene. So one care information is that PIDs do not measure health risk exposure. So this device has to be used with caution, and you have to know what it is that you are measuring. And I see a lot of people that misuse PIDs. Once the liner was installed, we saw a spike in readings, and we saw a spike in those readings in styrene readings. So I've already now converted the readings from where they were, and that is a styrene release. What we found during the steam cure of this liner, that most of the styrene was released during that curing process. So the styrene is cross-linking and forming a solid. There is some of it that goes into the air phase, but that was basically after 8 minutes, and after 20 to 30 minutes, it basically was all used up and there was no more styrene. So the release of styrene during the steam cure is relatively short on that period. So once the liner is cured, there's no more styrene to be released, or very, very, very little. So this diagram shows the concentration of styrene in water-filled traps and air-filled traps itself. What we can see in the water-filled traps is that there is styrene in the lateral before the water trap, but if you look at the trap itself, there's nothing coming through, and our concentrations are relatively low. Look, maybe 2 parts per million that have come through the water trap. So the water trap is a very effective barrier to keeping those styrene concentrations inside the lateral, and there's no health risk exposure because no one's going to be in those small little laterals on that side. So the traps do work. If we have an air-filled trap, the styrene does migrate out of that lateral, and if it's air-filled, it could go into a building. But then we have a faulty trap that's not working because it's not water-filled, and we don't have a proper trap. I'd also like to note that if the trap is air-filled and connected to the sewer, and gases are moving from the sewer into the lateral, then those homeowners have also been exposed to hydrogen gases and other sewer gases that also can be dangerous. So in this case, we're using the smell of styrene in the house shows that there is faulty plumbing in the house, and that the homeowners have been exposed to other risks. So again, another possible way that we can use this to as a good indicator that there's a problem. So last couple of slides, some of the key findings. PIDs only measure VOCs. We need to know what those VOCs are in order to be able to, and know what the concentrations of styrene in those VOCs if we're going to try to use a PID to convert it into styrene concentrations. So we need to know what those factors are. If it's a pure styrene, it's 0.43. If there's some other VOCs in there, there's probably much less than 0.43 as the ultimate on that side. We also use the water membrane sampler, and that measures the concentration that's absorbed over a given period of time. So we now actually have the health risk exposure. So the Waterloo membrane sampler is a very good device to measure health risk exposure of workers or in a given building over a period of time, and it's a very cost-effective way or an insurance that if someone complains of smelling styrene, you can actually measure what that concentration was and what their exposure risk was over a period of time. So again, it's a cheap and effective tool to determine both public and workers' health and safety. So those are things we found around on that side. Other key findings is that a P-trap will stop styrene from migrating out of the lateral. It will also stop the migration of sewer gases, and that's why it's part of the plumbing code, plumbing requirement. So if a house does or building does start to smell styrene during a CIPP operation, that house and building has had faulty plumbing that doesn't meet existing plumbing code often. Styrene is released early in the CIPP steam process. So if you are near the end in the manholes in those locations or during that, so it's relatively a short period of time. So again, the exposure concentrations are going to decrease with time. Exposure limits will be relatively short, not days or hours. So on that side, I don't think the health risk exposure is very low. For steam emissions or styrene emissions from the termination point of a CIPP liner or near exhaust, the main recommendation is to make sure that those people stay away from that area during the curing process. And once the liner's cured, the risk to anybody is relatively low. And again, the canary in the coal mine alerts you to that there's a plumbing problem and a possible exposure to dangerous sewer gases. I'd also like to point you to NASCO's website. NASCO has a safety site with lots of information, and the study that and the work that was done by the Transfer Technology TTC, and their publications and the stuff that are available and safety resources that are available there. Some of the key findings from phase 2 of their recommendation was to stay away from 15 feet from the steam emissions, because they found that those concentrations are very low, and therefore your risk exposure, regardless of how long you stay there, will be negligible. PPE and active air monitoring and entering storage containers or transport trucks is recommended. There will probably be an update on those requirements, and they recommend using these EPA assigned acute exposure guidelines for now, and using AGL 1 level of 20 ppm. So in my final conclusion is that health risk is exposure time times chemical concentration. We can have very high concentrations, but we could have 1900 ppm for a minute or relatively very short period of time. But we know that from the steam cure and the curing that the styrene is going to get used up. It's going to be converted chemically into something else. And there's not a lot of styrene after the cure is done, provided that we've got a proper cure, which happens. One way we can find out whether or not we have a proper cure is to make sure that we got our mechanical properties that we've had. We may have a slight smell of styrene after a CIPP liner is installed, but remember we can measure noticeable concentrations at 0.54 ppm, but that's well below the 20 ppm AGL1 limit. So if you look at your CIPP health risk exposure, especially to the public, if they're kept away from the job site during the cure, then the actual exposure risk to the public is negligible, unless they possibly have some issues with respect to their plumbing. So at this stage, I think I will I'll close out and take any questions that anybody has. George?
All right. Can you hear me, Mark?
I can hear you.
Excellent. So we don't have a lot of questions. One that comes up is, do you think there's a satisfactory level of understanding regarding styrene levels and setting the limits? I've seen we've seen some reports where the levels are very, very low, basically eliminating CIPP options for some applications.
I think that I'm not a toxicologist, so that's up to the toxicologist to develop, and what people seem to think are appropriate requirements. But right now, I would say from a legal perspective, from a litigation point of view, your mandate is to use best industry practices and guidelines. And I think that the court right now would assume that and use and accept 20 ppm AGL level 1 as an acceptable exposure limit for health and safety. If you look at NIOSH levels, they use they use STEL levels, which is a time-weighted average over 8 hours. Some other organizations use worker levels at 10 hours. So until there's some other study by some toxologists to the exposure risk, and until there's some other work that's being done on those levels. What I will caution is, how do you measure the styrene levels, and how do you know that what the styrene levels are? If you're using a PID to say what those styrene levels are, there's lots of misinformation around. They're measuring VOCs, they're not actually measuring styrene. So in some of their applications, and they don't quantify what the actual styrene concentrations are. So I would suggest that if you're really worried about it, then use some Waterloo membrane samplers and install them. They're very simple. You just take the tube, you put it in a little spring container, you open up the container, you record the time, and then you let it sit there in a room or out in a lateral, and then after a prescribed period of time, which could be 6 hours, 8 hours, or 10 hours, you cap it, and that will capture any styrene or any chemicals that go in, and then you can do a GC analysis to find out what the exposure risk over that time is, because we know what the uptake rate is for the chemicals to go in on that one. So I'd say be much more wary of being able to defend your measurements and the tools that you're using for your measurements, than as well as the concentration limits.
Okay, thanks, Mark. So just before we get into a couple other questions, I was supposed to talk a little bit about the upcoming CUIIC Pipeline Rehabilitation Academy, March 21st to 22nd in Mississauga. We'll have experts presenting a 2-day course that's designed to equip attendees with the knowledge related to asset management, condition assessment, maintenance, and rehabilitation of underground pipelines. You'll get a chance to learn about the most up-to-date advancements and new technologies to repair and rehabilitate the aging infrastructure. At this point, if you register before January 27th, there's a $100 savings on registration. And you can find the information on this on the CUIIC website under academy.cuiic.ca. So sorry I didn't mention that earlier. We have a few more questions. One, many homes have sewer smell issues. Is that normally dealt with prior to CIPP install? Is that done to limit the liability or minimize the liability after the fact?
I would say that if they have smell issues, the homeowner should have had those fixed well before the CIPP installation. So that's not part of the contract of the contractor to be able to do that. So in most CIPP applications and the laterals, the contractors will send notices and tell them to fill their traps to make sure that those traps are filled with water, and to mitigate making sure that these traps are dry. Again, those homeowners have been, the reason that traps are part of the plumbing code is to protect the homeowners from dangerous sewer gases. So that's on that side. As part of our paper that we published, we also looked at the modeling of how concentrations into the house. And we also, the concentrations of styrene in the house, if there is ventilation in the house and you start to smell styrene, if you open up the windows and open up the doors, those concentrations we have shown will go well below the AGL1 limits. So they'll be very, very low. And you have to have an exceptional case for the styrene to migrate up in the lateral. So most times the flow will go from the house down the lateral and into the sewer. So there's no gases that are coming up. So if they are starting to smell sewer gases, it's a unique application. They have some major plumbing issues. It's something that they should have fixed well before the CIPP operations on that one. And in that case, if it was me and I knew that they would have some smell issues, I would be a really good application for using a Waterloo membrane sampler. Go down, put the membrane sampler before you start the CIPP lining process, install it, open it, retrieve it after maybe 6 hours of it being installed. Put it in the trap or near that trap, and then you'll know what the exact exposure risk to those homeowners were. And if they want to move, make sure that they open up and ventilate the house, because that is also a critical factor. But the model that we used and the exposure risk is discussed in the paper. I just didn't have enough time to talk about it. Maybe we'll talk about that in a future webinar.
Okay, thanks. So Mark, when the Waterloo sampler, that's specifically for styrene?
No, it will work. It was originally developed for measuring benzene and toluene from gas spills in basements. It has different calibration factors and absorption rate for different chemicals, so we need to do a calibration curve. We've done that calibration work for styrene, so we know what the absorption rate of styrene is into that sampler. It has a patented membrane, so the stuff can't go back out. And so we just have to know what those correct calibration factors are. There's been a lot of work done because of work that we've done with Insituform in order to be able to calibrate those to make sure that we know what the styrene concentrations are. But it will measure anything, any gas will go in, and we can use a GC, standard analysis, to find out what other chemicals and stuff are in that sampler.
Thanks. There's a question about longer cure times when the product is installed in a harsh climate, northern Saskatchewan, Alberta, that will delay styrene vapor's release in a significant way.
Again, we found just in our study that the release happened once we got it up into a certain temperature with the thermocouples. It may you may delay. Most likely, I would expect, and that was my guess, my professional opinion at this time would be that you will delay the start of the release until that liner gets to a certain temperature where you start that cross-linking, and then once the cure is done. So I would expect that the release time is relatively the same. The thicker the liner, the more resin and the longer the time that you typically take to cure to get everything up to temperature on the inside as well as on the outside to get that cure. It's also a function of the type of resin. There are different types of polyester resin, and the cure time is provided by the resin manufacturer on those ones. So each resin may have a slightly different characteristics, but once the cure is done, there is very little styrene to be released.
Okay, thanks. One more question. Could styrene get into drinking water and affect taste by backflow?
There is, in a CIPP liner, is 100% epoxy, has no styrene. It would never, if it had styrene, it would never meet NSF 61 potable drinking water requirements or ANSI 61 drinking water requirements. So there is no styrene, and there's no way that any styrene can get into the drinking water. So in the CIPP liner, so there's no styrene to go in. So if you backflowed into a CIPP line, potable drinking water liner with a potable drinking with a epoxy liner, the probability of getting styrene in it is negligible or zero in an epoxy liner. So it is critical, and that's why I talked about the different types of resins. Drinking water is 100% epoxy solids with zero styrene. There are some vinyl ester resins that have styrene, but they're predominantly used for rehabilitation of force mains because they have better fatigue resistance. Again, if they do have styrene, they're used in vinyl esters are used in force mains, which is a sewer pipe, not a water main pipe. Vinyl ester resins that don't have styrene could be used possibly in drinking water if they can get NSF 61, but I'm not aware of any right now that has that. But again, they won't have any styrene. So I hope I answered that question.
I believe you did, but don't see any other follow-up on that. There are a couple more. We have another 4 or 5 minutes. One thing, Mark, there's a suggestion that can you update the release for the phase 3 study in NASCO? I believe it's somewhere in Q1. And there's also I don't know what SIRC toxicity study, what that stands for, but it's planned in release in Q2. Is that?
I'm not aware. I'm not part of those studies, so I don't want to give any information. I would contact NASCO or Dennis Piven or someone on the tech committee at NASCO through the website nasco.org, the safety group, and they'll be able to tell you, give you an update, or contact John Matthews, who I think leads up that study at the Trenchless Technology Center in Reston, Louisiana.
Sure. Okay. 2 more questions. The pipe lined in the study was 8-inch. Would the styrene emissions noted in the laterals be comparable if you're lining an 18-inch pipe, or do you think the emissions would be more?
In a thicker liner, we'll have more styrene because there's more volume of resin. What we did find, and I didn't mention this earlier, is that there is styrene in the laterals, but when you open up those laterals and you cut those out, we did measure the styrene concentrations the day after, and they had dropped to be negligible because of flow and concentration of moving that stuff back into the sewer. So those concentrations, if they were water filled in those laterals, dropped over a relatively short period of time. Some laterals had much higher styrene concentrations. What we found out that some of the when we opened up the laterals, there was some resin that wasn't cured in those sections of the liner, in those laterals that had moved up away, and it didn't have enough heat from a steam cure. So so that liquid resin that wasn't fully cured released higher, so those ones did have higher styrene concentration. So part of your process. If it was a hot water cure, the heat would go much farther. The exotherm, or the heat, the isotherm from the heating of the ground and everything would probably cure any of those resins, so you probably wouldn't have as high concentration and over a period of time, so they would dissipate. So, but eventually that styrene is lighter than air, so it wants to volatilize out of that liquid over a relatively short period of time. So those concentrations of styrene will decrease and degrade relatively quickly. So the bigger the liner, again, make sure you got proper traps. Make sure you got proper ventilation. That's why ventilation is done on the downstream side, is to get those gases out. They also now use a stack to make sure that any styrene emissions get up high, and they blow a lot of air through to make those concentrations lower.
Okay. Last question that we have time for, Mark, is could you comment on the use of CIPP in storm sewer situations and make recommendations for environmental protection?
Storm sewer applications. I did do some work in storm sewers with styrene concentrations. So again, you've got relatively short runs in culverts, if that's the application that if you're looking at culverts. So you have to look at the effluent flow on the other side. There is a ban in Ontario for by MTO. I believe that again is banned. That ban is not based on good science. That ban is around some initial short-term styrene concentrations that were detected on the downstream side. So from a CIPP in a storm sewer, there's no issue with respect to using a polyester resin. The health risk exposures, again, if you properly cure, is negligible.
I guess the one thing that might play into that would be containment of any of the cure water or the steam discharge.
Yeah, some people want to, if it's a hot water cure, contain that. One way to reduce concentrations in the cure water is to bubble it, put an air hose in, and you'll volatilize get the styrene out relatively quickly because it's lighter than water, so it wants to come out and will dissipate. I know that there's some other technologies that that are being looked at in order to be able to speed up that process, and so that when that water gets discharged on the downstream side, then to make sure that there's no issue. There is some confusion in the industry, especially in wastewater treatment plants, about styrene impacting the treatment bug process. I've heard that one many times. It's typically not, I've never seen any actual link to styrene. It's typically hot water cures where the water gets released that's too hot. It doesn't, hot water doesn't have any oxygen, and that can cause fish kills as well as bug kills in plants. But people have attributed to styrene, I think, wrongly, and primarily the water being released that's too hot.
Okay, thank you, Mark. I think that will wrap us up for today. We're just a little over the hour. Thanks very much for the informative presentation, and thank you all for joining and for the questions.
Yeah, if anybody wants a copy of the paper, please feel free to reach out, mark.knight@uwaterloo.ca, and I can send you a copy of our study. It's been peer reviewed and published, and if you have any comments or questions, then please feel free to ask.
All right.
Thank you very much, George. Thanks, everybody.
Thanks, Mark.